let's discuss solutions to the 1D heat equation with a set of different types of initial conditions. So the 1D heat equation that we have here are the n's immersed in ice water, and we have this as our solution after we use separation of variables. U of x and t is a sum over n, b sub n, sine of n pi over L x, times an exponential involving n squared, t, and L squared here. So let's just take the initial conditions that at t is equal to 0, the bar temperature as a function of x is 3 sine of 5 pi over L x. And we want to know what are the unknown coefficients, the b sub n's, and then what is the temperature of the bar as a function of time. Well, we can just plug t is equal to 0 in our general solution here, and then set that equal to our initial conditions. And when we do that, we'll find that the b sub 5 must be equal to 3, namely we can only need to pick up the n equal to 5 term. And b sub n is equal to 0 for n not equal to 5. Placing that back into our general solution, we have the temperature of the bar as a function now of time is the 3 sine of 5 pi over Lx, that was what it was at t is equal to 0. And then at later times, we just tack on the exponential with the appropriate n value. So we're choosing n is equal to 5, so that's where the factor of 25 is coming from in there. Okay, let's look at a slightly more interesting set of initial conditions. Let's look at a set of initial conditions where the temperature of the bar is 1 between L over 3 and 2L over 3 and 0 otherwise. And we want to solve for the unknown coefficients, the b sub n's, and then the temperature of the bar as a function of time. Well, we can do the same thing as we did last example. Set t is equal to 0 in our general solution, and then we set that equal to our initial conditions. Except now we can't just guess the b sub n's, we have to use a Fourier series in order to solve for the b sub n's. If we do the Fourier trick on both sides here, we'll find that the expression for the b sub n's can be written in terms of the initial conditions, u of x comma 0, as 2 over L, the integral from 0 to L, the u at t is equal to 0, times sine of n pi over L x. We need to integrate all of that. So we can just put in our expression that we have for the temperature of the bar at t is equal to 0. And so that means we put in 1 for that temperature, and now the bounds of the integral are L over 3 to 2L over 3, because otherwise the temperature is 0 outside of that region. And we can just do this integral, keeping track of minus signs and factors of L, and then canceling those. We need to evaluate this term cosine of n pi over L times x between L over 3 and 2L over 3. But we can do that, again, taking into account the minus sign, I get this expression for our b sub n's. We can now place this expression for the b sub n's directly into our general solution, and we have now the general solution for the temperature of the bar as a function of time. And it looks something like this. So we have some ugly looking coefficient. We can't seem to do much better than this on this coefficient, times the sine of n pi over Lx, and times the corresponding exponential for each n term. Let's take a minute to physically think about what the solution might look like as a function of time. So here's that solution, and then I'm just going to write it term by term. So let's write the n equal to 1 term, and the n equal to 2 term, and then, well, we could continue to write all of the other n terms. But I just wanted to point out, to write it out term by term here. And in particular, I notice when I look at the n equal to 1 term, and then n equal to 2 term, and so on, that one of the main differences between these, aside from the x dependence, the way the n factor affects the n dependence, or the x dependence, is that the higher n terms decay faster with time. There's an n squared up in that exponential. And so as I go to higher and higher n, those exponential terms decay even faster with time. So once I get beyond the n equal to 1 term, these exponentials are going to decay extremely fast with time. Let's see what that looks like in the actual time-dependent solution. So we can plot the initial conditions, or the temperature of the bar for the initial conditions at t is equal to 0. So here I just included, I think, about 30 terms in this infinite sum. If you include more, you'll get a sharper looking profile. This is, of course, an approximation to the initial conditions profile that we had said, because we're including a finite number of terms. And so now let's go to later times and see what happens. So at later times, say t is equal to 0.05, we see that the profile is smoothing out. The sharp edges of the profile are due to the higher n terms, the high frequency terms, but the high frequency terms are decaying really, really fast with time. So this is smoothing out with time. And in fact, if I go to slightly later times, then I get a profile for the temperature of the bar that effectively looks like sine of pi over L times x, the n equal to 1 term. So as I go to later and later times, it just looks like the n equal to 1 term, which will then decay to 0, as we expect, as t goes to infinity. So you can get some intuition for this, that namely, if you put an arbitrary initial conditions, set of initial conditions on this bar, at late times, the higher n terms are going to decay, and you end up getting the low n terms for what the temperature of the bar looks like as a function of time.